Hi, my name is Jonathan Mugen, and this is work that I've done with my advisor Ben Kuipers. So the world is a chaotic place. There's a lot of sensory input coming in, and it can be hard for a robot or an intelligent agent to make sense of it. One thing we can do is to track objects, and that helps us narrow down the large sensory input so we can get the locations of objects and the distances between them. And from that we can convert this huge input into a set of continuous variables that looks like this. Here we see the blue variables are the actual variables that come in from the environment. The red variables are the direction of change, or the derivative of those variables. And given both of these, we see the system in a much simpler form, but it's still very complex and hard to understand. And we'd like to get a robot that can learn to predict and control this system. So here's the environment that we work with. We have a robot sitting at a table with a couple of blocks, a couple of floating heads and a single block and a hand. It can't interact with the heads, but it doesn't know that ahead of time, and it tries to predict and make models of the environment and also tries to control it. And so we do that through QLAP. QLAP starts off with a set of continuous variables that we saw. It discretizes those variables in a way we'll see in a moment. It creates models of those variables, and with each model then it can find a discretization to make that model more reliable. With a model then it can convert the models to plans, and then plans are ways to form actions, and this forms a network of actions and plans that are the capabilities of the robot. We do this using a qualitative representation where that breaks the world into landmarks, and a variable can be in a location relative to a known landmark value. Once we have landmarks, we can create events, and then we can track the contingencies between events. If A occurs, then B occurs. And here we see the colors that give the reliability. In this case, yellow is a contingency that we pull out, and green is a plan, as we'll see in a moment. So here we see yellow, a particular contingency. It's pulled out, and it says A leads to B. Once we find A leads to B, then we can find new variables or situations where it's more reliable, and we can track statistics on that. And we see it's easy to track statistics because we now have a qualitative representation of the continuous input. Here we have the red showing the current values of variables. And this allows us to keep statistics and then refine the models. And so what we see then is once we've done this, we can take our models, convert them to plans, and we have this hierarchy because an action in one plan calls a high-level action learned by QLAP. And so what we see here is a simplified representation of the action hierarchy, the action network that QLAP learns while interacting with the environment. And so looking at the environment again, we see that the agent initially just motor babbles. But then, as it starts to learn actions, it can use those to practice. The interesting thing here is the agent learns autonomously, and then as it starts to learn actions, it tries to do them. Like in this case, it can hit the block off a table. And so after it's been learning for a while, it has its large repertoire of actions, and its exploration starts to look a little more organized. And so we didn't give it a task, we just told it to try to control your environment as best you can. And then after a period of learning, we can give it a task. We can say, okay, given what you've learned, can you now pick up the block, which in this case is hitting the top of the hand over the center of the block. And this is interesting because it takes a lot of sequential decisions in order to get the hand in just the right place. And we see that the agent has learned to do this, even though we didn't tell it to learn to do this initially. The end. Thank you.